Okay, so uh, good evening. Today we will discuss about the week 11 lecture videos. So in week 11, Professor taught about the further strengthening mechanisms like Taylor hardening, strain hardening, and dislocation interaction. So we will start with Taylor hardening. So Taylor hardening is the primary strengthening mechanism which results other strengthening mechanism like dislocation, dispersion, and other. So according to Taylor hardening, good evening, Athav. Can you see my screen? Okay. Okay, so today we'll discuss about some more hardening mechanism. So first we'll start with Taylor hardening. So Taylor hardening is the primary strengthening mechanism. So this relates the strengthening in uh, single crystal and polycrystal. And the mechanism in uh, uh, single crystal deformation and polycrystal deformation is completely different. So we'll discuss one by one. So for single crystal, if we want to draw shear stress versus shear strain, we are drawing shear stress versus shear strain graph just to show because the deformation occurs because of the shear stress and the uh, engineering stress strain behavior will be same according to this. So for single crystal, it starts from So so this is the stress strain behavior for a single crystal. So single crystal, we know we have a single atomic orientation, and in single atomic orientation we have only primary planes of a cube, like FCC and BCC. Okay, so we can divide this graph into three regions. First, second, and third. So in the first region, only slip systems which have the lowest critical resolved shear stress will activate first and deformation occur. Slip system with lowest CRSS activate and deformation starts. By so as only one only one limited slip system is ac- gets activated in deformation is in its initial stage. So there are very less amount of dislocations in the single crystal at the time in the stage one. So because of the low dislocation density, the strain hardening is very low, and as we move from stage 1 to stage 2, so in stage 2, more number of slip systems activate. Slip system means so this first slip system is for 111 and 110, 111 plane and 110 direction, and uh, more slip system will be variants of this slip system, means one bar one and the slip direction, and other slip systems which have less atomic planar density than 111 planes, they also activate. So the phenomena which uh, results in activation of those slip system is the dislocation density increase. Dislocation density increases because of the more slip system activation, and deformation continues. So in the second region, we can see the stress is increasing very sharply with the shear strain. So strain hardening is very high. Okay, so in the third region, we can see the shear stress is getting some constant value with increasing deformation. So we can say in the third region that some dynamic recovery means recovery during the deformation occurring, and recovery means the annihilation of dislocation because of their interaction. So the annihilation of dislocations will releases the stress, so that require less amount of stress during the deformation. So dynamic recovery occurring, and decrease strain hardening rate also decrease because there is no increase in stress with increasing deformation. So strain hardening is also decreasing. Some more points are there. So the uh, dynamic recovery and the uh, means the shear stress becoming constant is related to the cross slip and glide mechanism. So cross slip starts to take place and releases stress due to pileup. And uh, it the in the third stage, the temperature also plays a role in determining a deformation or in deformation. So as the temperature is uh, present, the climb process also will occur. That so because of the climb also, the stress release uh, is there, and in this stage, interaction of dislocations is chief hardening mechanism. So we will discuss now how the dislocation density increases and dislocation interacts with each other. So we know that in a yeah. So first we will so this is for the single crystal deformation. For polycrystal deformation, we cannot rely on single slip system for deformation to occur. So for polycrystal, shear stress versus shear strain graph looks like this. So in this, only second and third stage is there. So for polycrystal, uh, only one set of planes cannot deform, because we know there are multiple grains, and multiple grains are multiple single crystal. So the deformation will only start when CRSS or the applied shear stress increases to a value that reaches to CRSS of uh, more number of grains. So for this, minimum of two independent slip systems uh, is required for deformation uh, in 2D material. And if we talk about 3D material, which are bulk material, so for the 3D materials, a minimum of five independent slip systems required. So when applied shear stress reaches to CRSS values of five independent slip systems, then only deformation starts. So because there are means more than one slip systems activated at a time. So because of the deformation happening in all uh, slip systems, the dislocation density will increase very fast. So that's why in it starts from the second stage where the strain hardening is increasing, and after that, dynamic recovery starts in the third stage. Means because of the dislocation, interaction, and annihilation, the stress release uh, occur because of the different cross slip and climb mechanism. Okay, so the Taylor hardening can be uh, given as means these are the two dislocation. So the y and x distance between two dislocation uh, can give rise to shear stress of around alpha GB square root of rho. So rho here is the dislocation density. So as dislocation density increases, the shear stress uh, or apply means shear stress of the material increases, and that result into the increase in the strength of the material. Okay, so we'll discuss now how dislocation density increases. We know that dislocation lines present in material or in the single crystal. So if this is a dislocation line pinned at 2 points, or these 2 points can be grain boundary points or free surfaces. So if material is subjected to a stress, so if stress is coming in this direction, so this dislocation, because of this applied stress, dislocation line length increases. So it becomes like this, and after some stage, it becomes like means this dislocation line is increasing, and this dislocation line further increases to a point where the two uh, these curves meets at their point. So the line vector for these two halves are opposite in direction. So because of this opposite line vectors, there will be interaction between these two partials, and that will attract each other and become a this type of uh, line gets remain, and this dislocation line will detach from the primary slip line dislocation line. So this is the dislocation loop generated from this dislocation line, and this move forward in this direction. With time, this dislocation line further get straightened out in like this, and if further stress is applied continuously, so this process will continue and generates more and more dislocation loops. So as more and more dislocation loops are generating, so they will pile up at grain boundaries. Means if this is a grain boundary and dislocation loop is extending towards grain boundary, so they will get pile up as this. So because of the pile up, we studied in last lectures that pile up at grain boundary uh, result in hardening. Okay, so this is how the dislocation density increases. Second thing, dislocation interaction. So we know there are two types of dislocation, edge and screw. So there are four type of case where edge and screw dislocation interacts. So first case we study with when two edge dislocations are perpendicular to each other, if we draw two planes, first plane is this, and this is the dislocation line, and you can see B1 E. E for edge dislocation. So B1 is the Berger vector for this dislocation line, and on the second plane, the dislocation line is this with Berger vector B2 E. So both are edge dislocation, and their bu- uh, so the motion of this dislocation line is downward, and this dislocation line is moving forward. So at one point, when they come meet at this point, and yeah, Berger vector for this is B1, for this is B2, and the line vector for this is T1, and for this line vector is T2. So after when they intersect at this point, so resultant dislocation line will be like this. So as we know that the Berger vector for the dis one first dislocation is in this is parallel to Berger vector of dislocation 2. So the first dislocation will move forward with no alteration in the dislocation line. So this is B1E. But for the dislocation lying on second plane will extend like this. Means this is B1 and this is B2. So B1 will ex will give a shift to the this dislocation line in on the plane of B1 dislocation. So this is this is the dislocation one, and the dislocation two will look like this. So dislocation line got extended on the plane one. So this is B2E. So if we want to uh, means find the character of this extra half line, so we can one thing is that this extra half line is out of the plane 2. So the line vector will be this, and the Berger vector will be so for this is in this direction B2. So we this is the line vector and this is the Berger vector for this extra half line. So as the B2 and T2 are perpendicular on this plane, so means and this is out of the slip primary slip plane. So this is known as the jog, and as they are perpendicular, so the jog will be of edge character. Means if any extra, yeah. So one thing I missed, like if a dislocation line got extended by some length, so if that extra length of dislocation is is in plane, then it will call as the kink, and if it is out of plane, so we will call it as jog. Okay. So here it is out of the primary plane too, and of they are the Berger vector and line vector is perpendicular. So we have created a jog with edge character. So both kink and jog can have both edge and screw character. Is this clear? Okay. So this is the first case where two edge dislocations intersect perpendicular to each other. Next, case two, uh, where two edge dislocations are intersecting parallelly. So these are two planes, and one dislocation is B1E, and the second dislocation is like this. So the first dislocation is moving in this direction, and second dislocation is also moving in this direction. And so this is a B2E. So after when they meet at this point or intersect, so after interaction, the extra line formed will be like this. These are two planes. This is the intersection point of these two planes. So both dislocations. So dislocation one will be like this. This is B1E. So this get shifted by this extra half line in this direction, and the second dislocation will get extra line in on the same plane, means on the same interaction plane. This is B2E. So if we want to check, so both lines are on the plane, means we can say S2 and S1. So S1 and S2 are in plane. So they are of, so they will be called as kink. And if we want to check the character, if it is screw or edge, so we can say that this is B1 per, so S2 is parallel to B1, and its Berger vector is in this direction, means B1 or is also B. So B as S2 is parallel to B2. So means Berger vector and line vector are parallel. So we can call it as screw character. Similarly for the S1, Berger vector is in this direction. So S1 will be parallel to B2, and it is also parallel to B1. So both S1 and S2 extra lines are kink and of screw character. So I'm writing S1 parallel to B2 because the amount which is which by which it is shifted is equal to B2, means S1, the magnitude of S1 will be equal to the magnitude of B2, and here the magnitude of S2 will be equal to magnitude of B1. Okay, so this is the second case where two edge dislocations are parallel. So they will form two kinks of screw character. Uh, can you scroll a minute? Yeah, this is this fine or more? I have to shift more. Okay. Okay, then we will proceed to case 3. So in case 3, one is edge and second is screw dislocation. So this is plane, and at this point, dislocation line, this is screw dislocation, and this is edge dislocation on this plane. So this is moving towards the screw dislocation. So the Berger vector for this is B1E, and for the screw dislocation, it is B2S, S for screw, and E for edge dislocation. So as it moves towards the screw dislocation, so after interaction, so the edge dislocation will be like this, and the screw dislocation. So, so both gets displaced by each other. So as the B1 is moving on this plane, the B2 will try to shift this line in the upward direction. So this get shifted by this. So this is line vector T1, and this is line vector for this is T2. So it got shifted by, so this is T1, and so T1 will get shifted by the amount of B2S, and T1, as we know that the Berger vector is in this direction B1. So after interaction with the screw dislocation, B1 gets perpendicular to T1, and uh, it is out of the plane. So the extra line created is out of plane for the edge dislocation. So it will be jog, and B1 and T1 is perpendicular. So it will be of edge character. While if we talk about screw dislocation, So screw dislocation gets shifted by B1. So this is B1, and line direction for screw dislocation will be in this direction. So here for edge dislocation, the T2 the amount of T2 displacement will be equal to, sorry, this is B2 and will be in this direction. So this is the amount of screw dislocation gets shifted by a magnitude of B1, and it is in the plane. So not it is not in plane. It also so the extra half plane for the screw dislocation will be this. So this plane is means this displacement is on this yellow plane. So this is the shift of the screw dislocation is out of plane. So it is jog. We will call it as it is jog, and as T2 will be perpendicular to B2. So this will be of uh, edge character. Okay, so in case that where edge and screw can you hear me? Okay. So in the case that where edge and screw dislocation interacts, so both jog will form of edge character. So in case 4, which is last case, where two screw dislocation interact, or and they are perpendicular. So one dislocation is on this B1S, and this is the second dislocation. of buzzer vector B2, and the B2 is moving towards the B1. So after interaction, uh, so B1 will get shifted like this, and B2S. So the displacement of B1, or if we say it means because the line length is increasing, so we will say T1 and it is T2. So T1 uh, is equal to the amount magnitude of B2, and where the T2 will be equal to the magnitude of B1, and the line formation is for dislocation 1 is kink because it is on the this plane only, B plane 1. So because it is in plane, so this will be kink, and the line vector T1 is parallel to B1 because in this direction. So T1 is parallel to B1, so this will be of no, so sorry, the B1 will be in this direction and T2 is in this direction. So T1 will be perpendicular to B1. So the kink will be of edge character. While for the dislocation 2, it is displacing out of the plane, and this is T2 and this is B2. So T2 and B2 are perpendicular and it is out of plane. So this will be jog of edge character. Okay. So these are the four cases where screw and edge dislocation interact. So we will discuss the assignment questions now. Okay. Okay, so can you see questions? Okay. So first question says the three stages of deformation of single crystals are characterized by option one. Yeah, easy glide, strain hardening, and dynamic recovery. Second question is which of the following statements are correct regarding deformation in polycrystalline materials? Option two and four. Yes. And the third option is also correct, means as tensile loading starts, multiple flip system gets activated for deformation because 5 and 2 are multiple. So the third option is also correct. Third question say like determine the dislocation density for a FCC cubic crystal if it is deformed under a shear stress of 40 MPa, and we have to assume Taylor hardening to be valid, where shear modulus is 50 GPa and Poisson's ratio 0.5 and lattice parameter is 3.6 angstrom. So according to Taylor hardening, the shear stress is equal to alpha GB square root of rho. So this rho is a dislocation density. Alpha is a geometric factor. We can take it as 0.5. G is shear modulus. B is Berger vector and dislocation density. So we have given lattice parameter A 3.6 angstrom. So for FCC material, the Berger vector is generally equal to A by root 2. So we can take calculate the Berger vector from this, and if we put all values, so dislocation density will be tau divided by alpha GB and square of the whole term. So by putting values, 10⁻⁶ divided 0.5 into 50 into 10⁻⁹ into Berger vector 3.6 into 10⁻⁻10 meter and by root 2. So by calculating this, the dislocation density will be 7.79 into 10 raised to power 14 per meter square. So third option is correct for this question. Okay. So next question is we have to match the column with strengthening mechanism and the interaction at the uh, in that strengthening mechanism. So first is the solid solution strengthening. So in solid solution strengthening, the solute and solvent atom interact, and they can interact with dislocation also. So elastic interaction between solute and dislocation. So this will match with the second option. In strain hardening, lower coatal barrier are formed. Means lower coatal barrier are formed when after dislocation interaction. So if the jog and kink are uh, edge and screw character, and if they cannot move on their slip plane, so because they get immobile at that position, so that is known as the lumbar barrier. Immobile dislocation interaction uh, interactions. Third is grain size strengthening. So grain size strengthening is related to dislocation pileup at grain boundaries. So this will match to first dispersion strengthening. In dispersion strengthening, we have second phase particles and matrix. So the incoherency between these two will result in hardening. So first to second, second to fourth, third to first, and fourth to third. So the second option is correct for this. So next question is, what are the consequences of Frank Reed source activation? So Frank Reed source are the dislocation line only, which generates dislocation loop. This is the dislocation line. So they form infinite number of dislocation loops. So there. So how the dislocation loop and dislocation density are generating? So uh, in Frank-Reed source activation, dislocation density is increasing. So increase in dislocation density will increase the yield strength due to work hardening. So second option is correct for this. And the further dislocation generation and interaction will also form tangles. Dislocation tangles are also formed after the interaction of dislocation. So fourth option is also correct for this. Thus, sixth question, which of the following are the source of dislocation multiplication? So for dislocation multiplication, these Frank Reed source are the primary cause for multiplication. Accidental crystal growth from melt is also generate the dislocations. Means if there is any interruption in crystal growth, so that interruption in crystal growth also form dislocation. Third is homogeneous nucleation. So homogeneous nucleation, we know this is the melt in which small nuclei starts to form. So these nuclei, if will form crystals, and because of the arrangement between these crystals, dislocation generates. And third option, vacancy clustering, also result in dislocation multiplication. So all four options are correct for this. Next question is in a FCC metal, a pure edge dislocation D1 with a Berger vector A by 2 1 bar 1 0 on bar 1 plane intersects with a pure edge dislocation D2 having Berger vector of this. So we have to find which option is correct. So from seeing the Berger vector in planes, so B1 is A by 2 1 bar 1 0 and B2 is same A by 2 1 bar 1 0. So as Berger vector of both dislocations are same, so plane intersects with the, so as the Berger vectors are same, they will move parallel to each other. So the if when two edge dislocation are parallel and intersect, so after interaction, both form kink of screw orientation. So this is related to case 2. So S1 and S2 are kinks with screw orientation. So fourth option is correct. Next question is the slip plane for the dislocation formed via Lomer Cottrell barrier by combination of dislocation with Berger vector A by 2 bar 101 on 111 plane with another dislocation having Berger vector A by 2 0 bar 1 on this plane. So we have to find the slip plane for the resultant dislocation. So for, so for calculating this, so first we have to find the line vector for the resulting dislocation interaction. So line vector can be uh, obtained from the cross product of these two planes. One 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 and 1 bar 1. 1 minus 1. So this will give uh, a vector minus 2i plus 2j plus 0k. So this if we want to take the 2 common, so this will be 2 bar 1 0. So this will be the line vector after interaction after intersection, and the Berger vector for the resultant dislocation will be addition of these two Berger vectors. So this will be A by 2 bar 1 and 0 will be bar 1, 0 and bar 1 will be bar 1, and 1 and minus 1 will be 0. So this is the Berger vector, and the uh, slip plane will be cross product of this line vector and Berger vector. So line vector is minus 1 1 0, and Berger vector is -1, -1, 0. So this will give y plus 0j plus 2k. So this will be 002 plane. So 002 plane is option D. We can take out 2 also. So 001 will also be plane for this location. Okay. So next question is on the lower quartile barrier also. So a lower quartile barrier involves the dislocations from planes bar 1 1 bar 1 and 1 1 1 bar 1 bar 1 with Berger vectors these respectively. Which of the following reaction would result in lower quartile lock? So for a lower quartile lock, we have to see that which dislocation reaction is energetically favorable and the resultant Berger vector for this. So the third option, which is a by 6, this 1 2 1 and a by 6 2 1 1 will result in a by 6 1 bar 1 0. So this reaction is energetically favorable, means you can check other options also. So for the third option, the if you want to calculate energy, so the energy is uh, directly proportional to square of Berger vector. So this will be a square by 36 and 26 plus 2. So this will be a square by 6 plus a square by 6 will be equal to a square by 18. So this will be a square by 3 and a square by 18. So this the right hand quantity is less than the LHS. So this reaction is energetically favorable. And the Berger vector, which is 1 bar 1 0, is this lie on the plane of 1 0 0 plane, which is low low density plane. So as we know that dislocation move only on planes which have high atomic density. So that's why the this will form a lower quartile barrier. Means this dislocation is forms because it is energetically favorable, but this will not move and will not contribute in the deformation. So the third option is correct. Uh, the 10th question says the figure below show the intersection of two dislocation with line vector AB and XY across two orthogonal planes having their Burgess vector parallel to each other. Which of these statements are true with respect to this configuration? So in this case, we are seeing two edge dislocation. This is B1 and this is B2. So B1, B2 are in the same direction and both are edge dislocation. So two edge dislocation with the parallel Berger vector will generate king of screw character. So kink of screw character are formed uh, from this dislocation. So the second option, which says kink with screw orientation is formed in both dislocation AB and XY. So this is case 2. And one last question is there. So it says, which of the following statements about dislocation interaction and jogs and kinks are correct? So first option says when two edge dislocation intersects, the step formed S1 and S2 are of screw character and kinks and both add in glide. Add in glide means they are in plane, and the glide because in this same plane they are uh, primary glide plane. So uh, the extra half dislocation line, which are kinks, will further contribute in glide or deformation. So first option is correct. Second is when an edge and screw dislocation intersect, the jog formed on the screw dislocation is sessile and does not add in glide. So this is also correct because the jog formed on screw dislocation is out of plane, and that will get immobile after intersection. So this will not add in glide. So second option is also correct. Third option says when an edge and a screw dislocation intersect, the jog formed on the edge dislocation is glacial and adds in movement. So in this condition, the jog formed on the edge dislocation. So this is the case 3, related to case 3. So in that condition, this will be jog will be mobile. Means mobile and glacial are the same word. So the that jog adds in movement of or glide. So third option is also correct. And fourth option says when two screw dislocation intersect, the resulting dislocation line remains entirely within the original slip plane. So this is not correct because when two screw dislocation intersect, kink, no, not kink, jog of edge character forms, and they are out of plane. So fourth option is wrong. Only first, second, and third is correct.